today's video I want to talk about VQ-VAE, which stands for Vector Quantized Variational AutoEncoder, and I will show how we can train this model using a very common dataset in deep learning, which is MNIST, handwritten digits. So let's see how VQ-VAE can be implemented. So as usual, at first I want to import the Decoder libraries. Okay, so I need PyTorch. PyTorch version. Let's check the version. Then I need some other things from PyTorch. Then a neural network module, import optim, then data loader, import data loader. Let's create a few empty cells so there is more space. Then I need torch vision. I can also check the version for torch vision. From torch vision, import datasets and transforms. Torch vision dot videos, import make grid. Then from DQDM, import DQDM. NumPy is also required, and finally matplotlib. So I think these are all the required libraries. Let's make it capital. So I have a torch version of 2.0.1 and torch vision version of 0.15.2, and this is probably CUDA version. Okay, also next define the device. So let's at first print the GPU name that's available. Get device name. And new line. Device CUDA torch CUDA is available, else this will be CP. And device is device new line. So I want to check the total number of GPUs. Device count. So GPU is available and total number of GPUs is 1. Now it's time to load MNIST dataset. Training datasets, sorry, not this one, MNIST. So in this folder the dataset will be downloaded in folder data src, and this will train. Download to transforms to tensor. Control C, then test dataset, and in this case train will be false. Everything else remains same. Oh sorry, this is not capital, it's small. So now dataset is being downloaded. Okay, it's finished. Let's check the length. Training dataset. To copy, see the length of the test. This is test 60,000 training data and 10,000 test data. We can also check the pixel dimension. So this will be shape of the, so in that case data dot shape. So this is the pixel dimension of each image, 28 by 28 pixels. Let's visualize randomly selected samples from training dataset. Let's create few empty cells. So figure axis, and rows on and columns. Fix as 10 to dot random dot randint and training dataset. Training dataset dot data index CMAP will be, let's say, gray, and set title dot targets index. Let's say from size 12. I think this is good enough. x.axis dot false. So these are 10 randomly selected samples from the training dataset. You can do the same for the test case as well. So you just have to mention test. This will be test. Looks okay. Okay, so these are 10 randomly selected samples from the test dataset. Okay, now it's time to for I think define data loaders. So training data loader, training dataset, batch size, let's say 64, shuffle true, drop last also true, and in this case it will be test data loader. Test shuffle will be false, drop last true. Okay, now just copy these two to save some time and change into the data loader. Looks okay. Okay, so there are 937 batches in training data loader and 156 batches in test data loader, each with 64 images. Now let's create encoder class. So there are three parts in VQ-VAE. One encoder, then another is, the second one is Vector Quantizer, and last one is what is last one? Decoder. So let's first create encoder. Again, few empty cells. And dot module self super encoder here. Now sorry, this is wrong. I want to sequentially add some layers. Need to give it a name, so on one sorry and dot conf 2d in channels will be 1 because in MNIST images are grayscale images. Out channels, let's say 16, kernel size, let's say 4, let's try to padding 1. Add module, so in this case this will be patch norm. Num features will be same as output channels of the previous convolutional layer. Self.encode ReLU then I want to repeat these 3 layers one more time. Change the name. In this case the input will be the previous output, this one, let's say 32, so this will be now this output, and just only one more convolution layer, this will be 3. In this case input will be 32, output let's say 64. Kernel size will be 3, 1 by 1. Looks alright. Forward self x self.encoder x. In fact, let's just call it encoder out instead of calling it x. Return 𝑃𝑛C out. Now let's, did I import dot summary? I forgot to import dot summary. So from dot info import summary. Now let's check how the tensor shape changes in this encoder class. Before that I am to give it another name, so visualize encoder class. So input size will be batch size, in our case 64, the number of channels 1 input because grayscale images, pixel dimension is 28 by 28. Okay, so there are 7 layers, 1 2 3 7 layers, and when this input is passed to this encoder, this is how tensor shape is changed, and finally we get this one, and this tensor shape will go to the next Vector Quantizer class. Let's check that out now. So now create VQ class, Vector Quantizer. So class VQ. Vector Quantizer layer or section, there is an embedding table which is also known as Codebook. So this is created using the number of embeddings and the dimension of these embeddings. So in my case I will consider 256 embedding vectors, and it will have an embedding dim of 64, and this has to be the same of incoming, same as the number of channels of the incoming tensor. So this shape will be provided to the vector quantization layer. So the number of dimension will have to be 64 in this case. If it is like 128, then it will have to be 128. And there is something called commitment cost. Commitment cost. So this is multiplied with commitment loss. In the final loss calculation we'll see. So at first write the forward method. So self, this is the input. So this part is a little bit tricky. This is the original shape of the input. So batch size, channels, height, width. Then we have to put the C in the last dimension. So x will be x dot permute. So it's better if I write down some comment here. So 𝘵𝐶𝐻𝘊. Then we're keeping 0 fixed, 2 coming ahead, 3 coming ahead, 1 going to the last. So this shape is now becoming 𝘵𝘊𝐶. C is going to the last dimension. Then x dot shape 0. So this is kept fixed, -1 x dot shape 3. This is kept fixed, this is kept fixed, and we are putting -1 here, so these two will get multiplied. So shape becomes B H then multiply W C. Then distances with these codebook vectors are calculated. C dist self width. And repeat. Let's get empty cells. Repeat. X dot shape 0 1 1. So in this case the shape becomes 𝘵𝐻𝘊𝑁𝑒. NE is the num embeddings. So batch size, then multiplication of these two, and then this will become 256. Then after calculating distance, the index is considered that has of the codebook vector that has the lowest distance. So encoding indices will be toss dot argmin as inner dimension. So in this case the shape becomes P, HW. Because we are performing this argmin operation, it takes only one value, so this multi dimension doesn't exist anymore after this operation. Then quantized embeddings are extracted using these minimum indices. So toss dot index select. What dimension will be 0 and index will be encoding indices. Select dot view 1. Here the shape becomes, because of this operation everything gets like multiplied. So P H W E D, which is the same as embedding dim. So 64 quantized, and we have to check the, we have to reshape the X again. X dot reshape. So the last time X shape was this. Now we have to reshape. So we are keeping this one same. This one same, and previous also getting multiplied. So these three are getting multiplied. So the shape becomes B W, C. Okay. Now we can compute the loss terms. Loss dot mean and square it. Sorry, one bracket short here. This is the commitment loss, and another one is called codebook loss. Loss dot in quantized and as okay, and final loss value will be codebook loss save dot commitment cost, which is 0.25 according to the VQ-VAE paper, multiplied by commitment loss. So this is the entire quantization loss that we are getting from here. Then there is something called straight through estimator. Straight this is required because this argmin operation is not actually cannot be back propagated because of this argmin operation. So gradients are copied by straight through estimation. So quantized -x detach. The shape will be these three lines. I have no shape because these result in single values on loss value. Then after, so previously quantized had this shape. In this case also it will have this shape. So sorry, P H W E D or C, because both are 64 in this case. Then shape is changed again, quantized totally shape PHWC. This is our current if we consider this separately, then it becomes PHWC. We have to put it in this shape for decoder operation. So permute, this is permute. So now this C will go before. So the shape becomes BCHW again. And one more thing is Codebook indices. So we have this encoding indices. We will reshape it. So encoding indices have this shape. We'll keep this on fixed and separate these two. Quantized dot shape to dot shape 3. So that's all. Then we'll return this entire quantization loss. So at first we'll return the quantized latent embeddings, then the quantization loss, which is this one, and also the codebook indices. So let's see if everything is correct here. So this is VQ. So this section will receive this shape after the encoding operation. So 64 64 77. Sorry, some kind of mistake. Sorry, detach. Okay, there are many mistakes. Quantized. This is detach. Okay. So we are giving this shape as input and finally getting this as output. So the tensor shape doesn't change in this section, only quantization operation takes place. Okay, I think just mention this here. So visualize VQ plus. Finally, there is decoder class. So create decoder class. So class is decoder and dot module. decoder dot sequential, then sequentially add few layers, transpose formulation, in channels will be 64 because the previous output, out channels will be 32, kernel size will be 3, stride 1, padding will be 1. Cell dot decoder, then I have to add patch normalization, norm features will be the previous output 32, cell decoder, add module ReLU, and place will be true. Okay, so this is just my style. I mentioned the layer name in opposite order compared to the encoder, but this is not necessary. 1, 2, 3 can also be used and everything will work properly. Then copy, this will be 2, this will be 32, the previous output, 16, 4, 2, padding 1, and this will be the output channels equal to output channels, and this looks okay. Then patch normalization is not required, this will be 16, and finally we'll have only 1 channels because MNIST creates images. This will be 4, 2, so this will be 2, adding 1, oh so this will be 1, this will be 𝘓𝘓𝘧𝘪𝘯𝘕. I think it should be okay. So we'll get the output cell dot decoder and return out. So visualize decoder class. Summary, decoder input size will be the output of VQ layer. These are the discretized latent embeddings, and these will go as input here. So 64, 64, 7, 7. So finally we are getting 64, 1, 28, 28, which was our input to the encoder. So I think everything makes sense. Now I just want to put these 3 sections in one class, which will be called VQ-VAE class. So define class you can see here, just putting 3 sections together. VQ-VAE 𝘓.encoder will be encoder class 𝘓.VQ will be VQ class 𝘓.decoder. Forward self mix. We first get the output from then we get the quantized embeddings. Let's call it quant out. Then we also quantization loss, and we also get the codebook indices, which we do not need here, so I'm ignoring it for the moment. 𝘓.VQ encoder out. Sorry, this is wrong. Quant. Finally, the reconstruction from the decoder. We need to pass this quant out. Finally, return the reconstruction, which is out, and quantization loss, because we need it. We need to add this to the reconstruction loss for training the model. Let's see if everything works fine or not. Input is obviously the MNIST input. So this goes as input, and finally, after passing through 3 sections, we get the same output. Okay. Now, I forgot to give a heading here. So this is just visualize VQ-VAE architecture. Okay. Again, number 7 would be define the training batch. We have data, model, criterion, and optimizer. Model.train, then data will be device. We get the output and quantized loss from our VQ-VAE model as shown here, output and quantized loss. So this will be model data, then loss. Sorry, this is reconstruction loss. On loss will be criterion, loss will be reconstruction loss and quantized loss combined together. Then we have the usual 3 steps: optimizer dot zero grad, then loss backward, optimizer dot step, return loss. Define the test batch with torch dot inference mode, in this case model dot eval means we need, then we need these three or four lines. And return loss. Then set up model which is VQ-VAE, loss function, optimizer. So this is criterion. Model will be VQ-VAE, 2 device, criterion will be nn dot MSA loss, optimizer I will use the Adam, learning rate 0.001. Now it's time to train this model. Setting all sorts of seed, any box. I will only train it for 15. Test loss, for data, ignoring the labels, training data loader, batch loss, training batch. So this is model, array training losses dot mean. Same for the test data loader as well. Optimizer is not prepared here. Best loss dot, so this will be TSD batch loss. Test losses. Training loss dot event. Evoke as on any books. Training loss so need the test loss. And for if there is no mistake, then it should work. Okay, there is obviously mistake. Oh, sorry, forgot to mention in. Now it's working. I don't think this will take a lot of time. Something is wrong. Why am I getting all the negative results? It doesn't make sense. This is wrong completely. Okay, so there is some mistake here. So extra parenthesis is required. Let's run again from the beginning. Let's see if this works. Now it's more like it. So the problem was here. The problem was in this line. I forgot to put extra bracket here. On bracket, sorry. This bracket and this bracket. I forgot to put it, and that's why awkward results were obtained. Now it's make more sense. Okay, so maybe within a minute it will be finished. Okay, it's not bad. In the last two epochs it decreased significantly. In the middle it didn't decrease a lot. Anyway, so I think training is finished now. Let's plot model loss. Arrange in epochs. Fix size 74. Training loss also I have to plot the test loss. This will be blue and dotted line. Then what else is required? LT dot title loss curve. Font size 23. This is capital. Number of epochs. Label will be losses. PLT.xtx. What will be the font size? 12. YTX and PLT.legend font size 15. So this is how the loss curve looks. So it decreases sharply, then remains quite same, then in the last two epochs it decreases sharply again. I think if I mention n here, then probably all the epochs appear. Okay, now finally one more thing to do, which is model prediction. Randomly selecting 25 samples from the test dataset. Zero, for I in random indices. reconstructed. We get the output from and also the quantized loss, which is not recorded here. Then large grid, make grid, select random samples, CPU, and will be 5. Then another is reconstructed grid. This will be reconstructed. We can also see the code book. So from the encoder we get the quantized vectors, quantization loss, and codebook. I do not need the first two. I am gonna name it codebook learned. So model.vq, inside it will be model.encoder. Select random samples. Codebook learned. One is quiz. Sorry, this will be one. Codebook grid will be make. CPU and drop 5. It should work. Oh, something is, oh, again the same mistake. Detach, again the same. Now only one more cell block. Fixed size will be 12.6. plt.subplot number of rows, columns, and this is the index. plt.imshow, that must have the original grid. Permute onto 0. plt.axis, this is false. plt.title, original. Font weight, bold, color, what color? Let's say coral. Then just copy paste and change. This will be position 2, reconstructed grid, reconstruction. Yes, I think it's okay. Let's just change the color. Magenta, plt dot, oh sorry, just copy paste. This will be the last one, which is our codebook grid. This will be just codebook. Instead of coral, what color? Let's say olive. Okay, so this is the last cell block. So randomly selected 25 samples from here, these two lines. Sorry, then we are just sending it to GPU using this line. 362, this is probably 7 or 1, I am not sure. most probably 7, 9, 1, 2, 2, this is on 3, 7, 4, 9, 7, 4, 2, 1, 7, 5, 7, 1, 1, 2, 6, 7. Okay, and this is the corresponding reconstruction of these original images. Since this is not a complex dataset, it doesn't look too bad. The learned codebook could have been much more better. It kind of looks very scattered at the moment. Maybe we should train for few longer, then this codebook would appear much better. Currently they look quite scattered. Let's run it one more time to see what happens. Okay, now I just ran it one more time. In this case, the loss values also look lower than the previous ones. So in this case it makes more sense. So let's say for example this is 1. If we look at the codebook, which are the learned indices, this also looks like the shape of this digit. Then this is slightly tilted. This is also looking tilted. Same for this one as well, tilted. This is straight, this is straight. So this is 0. This also looks like has a shape of 0. So in that case it makes much more sense than the previous one. So I think 15 epochs are not enough. Probably 30, 40 or even more you can try if you want. But this makes more sense than the previous one. Okay, unfortunately this video became too long, so I want to finish. Thanks for watching this video.